Hi, welcome to the second part of lecture 8 of EEE 157, Communication Systems and Networks. In this part of the lecture, we will be detailing our discussion on the sampling process, and we'll talk about three different modes of sampling: your ideal sampling process, natural sampling, and the pulse amplitude modulation. Okay, so first things first, we want to understand the frequency content of your sampled signal and model it using equations, of course. So why do we need to know how a sampled signal behaves in the frequency domain? Well, if you want to know how it's going to be recovered and how it's going to be distorted through a channel, you need to know its frequency content because it's easier to process and analyze signals in the frequency domain compared to your time domain. Okay, so consider a message signal m of t sampled at a uniform rate 1 over ts. What does that mean? Every ts seconds, you get a sample of the signal. The sampled signal can be represented by this equation right here. So basically, you have a delta function every ts seconds. That's what this represents. Okay, a delta function every ts seconds, and it is scaled by the value of the message at that point. At that point in time, at a given point in time, and so on and so forth. To visualize that, you have this graphic here at the bottom of the slide. You have some smooth, continuous m of t analog signal, some arbitrary shape, and you multiply it by a train of impulse functions. Okay? When you do that, since due to the property of impulse functions having zero width, as you can see here, okay, so when you multiply your message to an impulse train, you will get this resulting signal right here, which is an impulse train whose mass or whose height is scaled depending on the value of the message at that time. And you now have your sampled message signal right here. So how do we analyze the frequency content of that sampled message? Feels complicated, right? So let's break it down. First, we need to examine the frequency content of the impulse train. So the impulse train is the sampling signal. We multiplied it to the message signal. When we do multiplication in the time domain, we perform convolution in the frequency domain. Sounds hard, right? So you will see why we're doing this. First, we need to get the frequency content of your sampled signal. Since it's a periodic signal, your sampling signal, so the impulse train is a periodic signal, we want to get the Fourier series. The Fourier coefficients of your impulse train can be obtained using your Fourier series analysis equation. So this is your analysis equation, okay? And by the property of your delta function, all of its value is concentrated at t is equal to 0. So this integral right here will just be the integral from 0 to ts, okay, of delta of t dt, okay? And your e here disappears since the value of delta of t is only concentrated at t is equal to 0, then this e will be e to the 0, and that will just be equal to 1. So you're just getting the integral of this, which is by definition equal to 1. Okay? So since all of this is equal to 1, then your uh, your Fourier coefficient is 1 over ts for all k. So you have a constant Fourier coefficient of for your impulse train, and you apply that to your synthesis equation right here. So your impulse train can be expressed as a summation of e to the j 2 pi kt divided by ts by definition of your synthesis equation. Okay? And when you get the Fourier transform of this summation by applying the time shift property, and sorry, by applying the frequency shift property rather, and the linearity property of your Fourier transform, you will obtain this Fourier transform of your impulse train, which is basically a delta function, an impulse function rather, an impulse train function also. So the Fourier transform of an impulse train is also an impulse train. That's it. we already have the Fourier transform of an impulse string. Quite simply, it's also an impulse string. The difference is that the spacing is 1 over t sub s. So your sampling signal, your impulse train at the time domain, is sampled every ts seconds. In the frequency domain, your Fourier transform, so the frequency domain, your impulse train has a repetition rate of 1 over ts, the reciprocal of ts right here. And it's kind of related to the scaling property of your Fourier transform. If you have a higher ts, you have a lower 1 over ts. Okay? So you have an impulse train in the frequency domain. What do we do with that? Now we have the frequency content of your sampled signal. Since we made the multiplication, we multiplied in the time domain. In the frequency domain, we will convolve. So to obtain the spectrum of your sampled signal, you have to convolve the spectrum of the message signal with the impulse train right here. Okay? So when you do that, you're convolving, let's say, uh, the frequency content of m of f is, or m of t rather, is contained here only. Has some bandwidth. Okay? When we convolve that with a series of impulse functions, by the shifting property of your impulse function, you will get a series of m of f's here. You have a train of m of f's that are in the frequency domain. Okay? So this is your original message right here, centered at 0. It's still the same right here, centered at 0. Same bandwidth, same shape. But some replicas appear and they're centered at 1 over ts and negative 1 over ts, and so on and so forth. There's also a replica here at 2 over ts. There's also a replica here at negative 2 over ts, and so on and so forth. Basically, they're replicas. What are these? These are the aliases. Okay? By sampling a signal, you're producing aliases of that signal centered at an integer factor of your sampling rate. Okay? So if your sampling rate is very low, so you have a very fast sampling, if your sampling rate is very low, the more space is there between your original signal and your aliases. Okay? And that's how we recover your sampled signal actually. We're using a low-pass filter. If we use a low-pass filter, as you can see here, some ideal low-pass filter, we are rejecting the high-frequency components and preserving the original signal. Okay? And since we're multiplying a rectangular function in the frequency domain, it becomes a convolution in the time domain. Since the Fourier transform of a rectangular pulse is the sinc function, then if we use the sinc function to, if you convolve the sinc function to the message signal, we're able to recreate the original message from the sampled message. And this is your reconstruction formula, and that's where the reconstruction formula came from actually. Okay. Now, if you sample too slow, the replicas will overlap with each other. Okay. And when the replicas overlap with each other, if we try to recover the original signal, you will only be getting this signal shape right here, which is not the same shape as your previous signal, the original signal. And this is already some form of distortion. So ideally, you want to space these replicas as far apart as possible. Okay? Once you do that, you will be able to recover your signal without distortion. Okay? And that is the Nyquist sampling theorem. And you've already encountered this. Okay? And these are just the conditions for Nyquist sampling theorem. Your message should be band limited, and your sampling frequency should be greater than twice the bandwidth of your signal. Okay? So for the equality, it doesn't hold for all cases. Spoiler. And this is how it doesn't work. If you have a sinusoid exactly at negative omega and positive omega, if you try to sample that using exactly the same sampling rate, these two signals will overlap with each other. The one at negative W and positive W. And this addition could overlap constructively or destructively depending on your sampling. But bottom line is that you won't be able to recover your original signal. Okay, so some notes about that. X of t, so the modern revisions of the Nyquist sampling theorem, x of t must contain no sinusoidal component exactly at b, or that b must be strictly less than half the sampling rate. And in practice, your message may not be band limited, so we use an anti-aliasing filter first before sampling the signal. So before you sample, you pass it through a low-pass filter so that any high-frequency components will be deleted first before you sample the signal. And in practice also, an ideal low-pass filter is not physically realizable. So we are actually required to sample more than the Nyquist rate so that we can increase the separation between the replicas. So if we increase the separation between the replicas, we can use a physically realizable LPF that will reject the high frequency components and maintain the original message right here. And you will encounter this when you will be simulating the sampling process. Okay, so now let's move on to practical sampling methods. As you know, an impulse function is also not physically realizable since it needs an infinite bandwidth. So one impulse function actually needs an infinite bandwidth, which is not practical for real-world systems. So we have devised two different types of practical sampling methods. We have the natural sampling and your pulse amplitude modulation. What's the difference between them? Your natural sampling will just be multiplying your rectangular train, your rectangular pulse train, instead of an impulse train, will be multiplying a rectangular pulse train to your message signal. So it's similar to the ideal sampling where you multiply an impulse train to your message signal, right here. For pulse amplitude modulation, you will sample the signal at some t sub s, and then you will hold that signal until the rectangular pulse will go back to 0. So sample this again, hold the value, sample again, hold the value, and so on and so forth. So that's the difference between them. We also call pulse amplitude modulation, it's also called sample and hold. Okay? And a rectangular train can actually be physically realized. You can physically realize a rectangular pulse train compared to an impulse train, because it has a finite bandwidth and so on and so forth. Practically a finite bandwidth. Right? Theoretically, it has an infinite bandwidth, but practically it has a finite bandwidth. Okay, so first, let's look at the natural sampler. So basically, just multiply the message signal with the sampling signal. The sampling signal can be modeled as a summation of some pulse P of t. In this case, P of t is the rectangular pulse train, but you can actually use some different pulse shape. You can design a different pulse shape depending on your bandwidth, but that's for more advanced courses. For now, let's assume that P of t is a rectangular pulse rather. If you want an ideal sampling, the ideal sampling case is that P of t is just equal to delta of t. So you can see that there's actually a similarity between your ideal sampling and natural sampling. Okay, so the sampled signal looks like this. Okay, so the naturally sampled signal can be expressed like this. Since we have a pulse train that is periodic, okay, we can get its Fourier series. In this case, it's just a rectangular signal. Quite simply, the Fourier series is defined by a sinc function. It's a sampled sinc function. Right? So a sinc function that is sampled ideally in the frequency domain. So we get the Fourier transform of that based on this definition. In the same way that we got the Fourier transform of an impulse train, we have a weighted sum of delta functions in the frequency domain. Okay? So the next step is, since we have a multiplication in the time domain, in the frequency domain, we have a convolution. So if the message signal looks like this, and the sampled signal, as we know, looks like this, the sampled signal will look like this. You have replicas, again, at the same points compared to your ideally sampled signal. You have replicas of your original signal, but their height is not the same as compared to ideal sampling. That's the difference. The height of the message signal, let's look at it closely. The height of the message signal right here depends on the height or the value of the sync function at that point. As compared to your ideal sampling, if it's an ideal sampling, then the height should be the same. Okay? That's the difference between your natural sampling and ideal sampling. Excuse me. The original message is still located at the middle of the spectrum. And you can easily recover a naturally sampled signal by using a low-pass filter. So if you want to separate the aliases or the replicas away from each other, then you use a smaller sampling rate. Okay? A smaller sampling rate would mean that your sync function will also be wider. Okay? And the drawback of that is that, as you can see, it uses more bandwidth. Okay? It uses more bandwidth compared to your analog signal right here. Okay? And when you sample it, again, when you sample it faster, you'll have a wider sync pulse and you'll be using more bandwidth and so on and so forth. And this is your natural sampling process. Okay? A pulse amplitude modulation, also called a sample and hold, as I've detailed earlier, is that every t sub s you get a sample of the signal and you hold it. And this is more practical compared to natural sampling when we talk about digital systems. Once you sample a signal, you should hold that value until your computer will be able to store it. So unlike the natural sampling, within a sample, as you can see here, let's go back a little bit. Within a sample, your signal changes. We can't use that in a quantization. So if you want to quantize a sample, you need to hold it first. And this is used more in digital systems. So what's the natural sampling for? It's used by analog systems that uses time division multiple access, and more of that in your more advanced courses. But natural sampling exists for now. Okay. So pulse amplitude modulation, on the other hand, holds the value until the pulse signal goes back to zero. Okay. For excuse me, for your sample and hold signal, or pulse amplitude modulated signal, or PAM signal, your sample signal can be written in this form. Okay, similar to how we wrote the ideal sampling case. But in this case, your amplitude of your pulse is constant within one symbol period. The ideal sampling case is when the pulse is equal to delta of t. Again, we can use any pulse shape p of t here. In this case, only we'll use a rectangular pulse for simplicity. Okay? So more advanced designs use different pulses to reduce the bandwidth of transmission. Anyway, okay. To obtain the frequency spectrum, since we recognize first, rather, that your ms of t, your sampled signal, is the convolution between the pulse shape and the ideally sampled signal right here. So if you perform convolution, we get this original expression right here. Excuse me. But your sampled signal here can also be expressed as a convolution between your pulse and your ideally sampled signal. So what does that mean in the time domain? Sorry, in the frequency domain rather. The time domain, you have a convolution. The frequency domain, so in the frequency domain, we have quite simply just a multiplication. So if p of t right here has this shape, it's a sync function, okay? And this is your ideally sampled signal. the frequency spectrum. You multiply that, you get this sampled signal right here. Let's zoom in on that. So compared to your natural sampling, okay, compared to your natural sampling, your signal, original signal here is actually distorted due to the shape of your pulse in the frequency domain. Okay, and it looks similar to natural sampling. But when you look at the frequency spectrum of natural sampling, it looks similar. Let me just clear that. It looks similar to sample and hold. So natural sampling and PAM are actually what we call duals of each other because their behavior in the time domain and frequency domain are opposites of each other. So natural sampling in the time domain becomes sample and hold in the frequency domain, as you can see here. And the opposite happens to PAM. PAM in the time domain becomes natural sampling in the frequency domain. Right? The problem with PAM here is the original message is distorted because of the shape, because of the shape of your pulse P of t. Okay? And the rule of thumb here is if you want to minimize the distortion because of this pulse here, your pulse width should not be greater than 10% of your sampling frequency. This is the rule of thumb. Okay? You can, of course, exceed that if you want to design a system, but you need to use some advanced processing at the receiver. So more of that in your higher courses. But you need to have a more advanced processing at the receiver so that you will be able to recover your signal without distortion. Okay? So if you don't want a distortion, then less than 10% of your sampling, your pulse width should be less than 10% of your sampling rate. However, that uses a higher bandwidth. So there's a trade-off between them. More of that in your higher courses. We won't talk about it here. Alright? So just to summarize, okay, your sampled signals have a larger bandwidth compared to their purely analog counterparts. We've shown this by looking at the frequency spectrum between your analog signal and your sampled signal. As a sampled signal's bandwidth increases if you use a larger sampling rate, but it's easier to recover the original signal by low-pass filtering. So since we're relaxing the requirements of the low-pass filter, we're able to recover it easier. And as you all know already, the minimum sampling rate should be twice the maximum frequency. Okay. So the difference between natural sampling and pulse amplitude modulation has been laid out earlier. That natural sampling in the in the time domain becomes PAM in the frequency domain, and PAM in the time domain is natural sampling in the frequency domain. And the nature of that is your natural sampling technique can be easily recovered without distortion, right? But it's not ideal to be used in a digital system since we want the computer to have time to process the sample before the sample goes away. In natural sampling, the signal always changes within a sample. But for your PAM, the signal does not change within a sample. But however, the trade-off between that is there's an inherent distortion in the signal because of the property of your PAM. If you hold the signal for within the pulse period or within the pulse width, the frequency domain, as you can see, distorts your original message signal at the middle of everything. Okay, so that's the inherent distortion of your pulse amplitude modulation. So we can use it for digital systems since the signal value is constant. The quantizer will have an easier time to quantize your sampled signal. So there you go. That's the end of this part of the lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Okay? Thank you for attending this session. See you next meeting.